to talk is from University of Warsaw.
Okay, so this is the joint work with two persons from University of Warsaw. I am not from the university. I work for Polish Academy of Sciences. And okay, okay, I have to do it manually. Okay, so the outline of my talk is the following. I would like to first discuss the self-similar solutions of vortex motion under the localized induction approximation. Then I want to show how these solutions can predict generation of vortex ring cascades after the single reconnection of vortex line at tiny angle. And then I want to use these cascades to calculate the dissipation of vortex tangle in the limit of temperature going to the zero. This is still, I think, open question when we have the quantum vortex tangle and temperature goes to zero, how the line length can be lost, how the tangle can dissipate. So maybe I take the stick. So after the Carlo talk, I have little to done. This is the way how we parameterize the vortex line. So this is S vector dependent on arc length and time. The equation of motion is the following. This is the self-induced velocity, which can be given by Biot-Savart law. This is the bulk velocity of superfluid component. And in the case when temperature is not zero, we have the friction term, friction component of velocity, which comes from the interaction of quantum vortices with the normal fluid. So it depends on the relative velocity of the self-induced velocity of the vortex to the velocity of the normal fluid. Now we can pass to the local induction approximation, and everything simplifies. So here we have the self-induced term, which is along the binormal, local binormal to the vortex like this, and then we have this dissipative term, which moves the vortex along normal. So this dissipative term makes that when we start from the vortex ring, it will propagate and shrink. So it will move on the cone. And when we take the wriggling, the wavy lane of the vortex in a shape of the lane, it will try to smooth all these kinks, right? Because there will be a motion in the direction of the node. So this coefficient alpha, this is the non-dimensional friction coefficient. It is temperature dependent, and it is non-zero for temperature greater than zero, but it quickly decreases with temperature, and for temperature smaller than 1 Kelvin, it is less than 0.01. Okay, so now I am changing the notation a little bit. This is, I am putting this beta, the coefficient of motion proportional to the circulation, to the alpha. So here there will be only alpha. This is just for technical reasons. Okay, so having these equations, it is interesting to look into the self-similar and the second class is quasi-static solutions. This is my earlier work. I want to discuss it briefly because it is important for further analysis. So this is the equation of motion. If we don't know how to solve it, we can pass to two scalar equations for curvature and torsion. This is differential integral equations. They look rather difficult, but to solve, but you can a little bit simplify them, not really very much, if you will search for self-similar or shape-preserving. I would prefer to call it shape-preserving solutions, which have that form. So this means that the vortex, this term proportional to square root of time that the vortex expands. This is just the homothety transformation, and this is the rotation. So still you get nasty equations, but in some cases you may solve them analytically, and the simplest case is when the motion of the vortex is equivalent purely to the homothety transformation. In this case, you can solve it not explicitly, but still in an analytical form. So what is important for the further analysis is that these solutions have self-crossings. This is LIA solution, so it may have self-crossings for when the angle between these two asymptotic lines is smaller than 8 degrees, and this non-dimensional friction coefficient is sufficiently small. I will give you the details later. Okay? In general, these shape-preserving solutions may have very curious structure. They are basically logarithmic spirals placed on the cones. There is a family, fourth parameter family of these solutions. It looks as a joke, but sometimes this joke is realized when you, for example, look into the vortices under the aircraft. So this is not purely joke. Okay, when I was doing this work, I was not aware about the Badke solution, which is a self-similarity solution exactly for alpha, for the non-dimensional friction coefficient alpha exactly equal 0 when this equation is integrable. And these solutions look quite different to the solutions I found for alpha larger than 0. And it is not obvious that this is a limit of these solutions, but it finds that this is a limit in some sense, of course. This solution has a constant curvature, not constant in time, but constant with respect to arc length. And of course, these solutions in time have changing curvature, but also the curvature decreases to 0 as we propagate from this cusp, right? So the only convergence, so the only convergence may be local close to this cusp, and this is in fact when we calculate this for large friction, and when we go to small friction, this red is almost undistinguishable. But when we go away, then there will be a difference between our and Badke solution. This is clear. Okay, so now there is a question if this is rather intuitive, but still worth to check if these self-similar solutions are reached when we do the LIA simulations, starting from the angle which is a little bit smoothed at the end, right? So it should work better, but okay. Oh no. Okay. So I will go. I have to go back. No, this is something I didn't expect. Okay. Yeah, but yeah, the changing resolution is something. Okay. No, this is. Okay, I think this is that simulation. Okay, so you can basically see that this structure can be reached, and maybe I skip the next one when you can. No, I think it is worth to show it. I think it is worth to show it. If I find it.
No, on the right. On the left of your screen, right, Forrest?
Left.
Yeah, go on like that, go on.
You think it is this?
This? Yes.
No, this
No,
is.
it's not the one.
Yeah, okay, this is this one because it shows that if we run LIA simulation, of course, in doing LIA we may have self-crossing, we obtain the structure with self-crossing. So it suggests that all information about the behavior, the local behavior of the motion is given by the asymptotics. I mean, it is given by the angle of these two lines. And everything will, in the case of alpha greater than 0, will be dissipated, and in the case of alpha equal 0, will be radiated away. So all the information is in the angle between two asymptotic lines. Okay. So now it is worth to check if these self-crossings persist if we run Biot-Savart simulations. Of course, when we encounter self-crossing, we will reconnect these lines, and this is the case. I'm sorry, I will do it once again that way, trying to find it. I hope it is this one. Okay, so this is not in the order. This is the relatively large angle, 8 degrees, when this formation is very small. Maybe I will show them one by one, not switching to the. Okay.
All these are Biot-Savart?
Yeah, they are Biot-Savart simulations. Okay. It goes once again. So you see that it is so that it propagates. One ring is formed, and then next ring is formed. Maybe once again. Yeah. Then it is smoothed, and the subsequent rings will be larger and larger. And if these lines are straight, then you will get the cascade of rings.
Just 4 minutes.
Okay. Oh, that's bad. I think I started a little bit later. Okay. Okay. So in fact, in Biot-Savart simulations, the angle can be greater than the angle below which the rings are generated can be greater than the angle predicted by LIA. And for a large alpha, this difference is rather large. So next, what we can do, we can go to the Gross-Pitaevsky simulations, because in fact, in Biot-Savart simulations, we cannot make any reconnections. So when we go to I think it is
At the top,
Okay.
second one.
okay. I'm sorry for the flashing. This is the face of C function. So you can see the formation of rings. Okay. So what we observe is that regardless of the computational method, Biot-Savart or Gross-Pitajewski, we can observe the cascade. In the case of Gross-Pitajewski, the calculations are more difficult, so we can see up to 2 rings. The similar result was obtained by Bob Kerr and presented, but he started from the parallel lines. And I think that this can still be explained by the solutions coming from LIA. When we start from parallel lines, we have something which can be called quasi-static solutions. Simply, this loop propagates, and when we calculate the self-crossing, we can find that when alpha is sufficiently small, we have self-crossings, and that the number of self-crossings tends to infinity when alpha goes to 0, which explains when we start from parallel lines, we get immediately series of rings. They are not one after each other, but they appear immediately same time, because okay. So now at the end, I want to discuss how this can explain the energy dissipation, the potential mechanism of energy dissipation in the limit of temperature going to 0. The idea is not new. Carlo Barenghi and David Samuels, they studied the evaporation of packet of quantized vorticity by rings generation. However, our mechanism is different because at every reconnection, we get the cascade of very small rings starting from atomic scales, which can penetrate even big tangle of vorticity. This mechanism is perfect when we have the localized packet of vorticity. So to do the calculations, we should notice that the length of the rings form the geometric cascade, the separation times form the geometric cascade. We can calculate the line length loss, which is proportional to time. Then, when we do the more realistic calculations, assuming that the reconnecting lines are not straight, but have the average curvature of the vortex line in the tangle, and stop this process when this angle between two lines becomes larger than the critical, we can calculate average line length loss at each reconnection at sufficiently small tangle when at sufficiently small angle. When the tangle is transparent, I will tell you what does it mean. Then all this line will evaporate and will annihilate possibly at the boundary.
Do it in 1 minute.
I will try. When the triangle is opaque, only a fraction, only the smallest of rings will be able to reach the boundary, and some of them will be captured by the tangle, so they will reconnect, so they will be not lost. And again, we can calculate the line length lost in the case when tangle is opaque, and then we can reach the line length lost equation for transparent and for the opaque tangle. The key parameter here is the fraction of reconnections which lead to the cascade of vortex rings. If this fraction, which appears here and here, is large, then this mechanism will be efficient. remember that we need reconnections under the very tiny angle. So if we assume that these angles are uniformly distribution, then the fraction of reconnections leading to the production of vortex rings is 10 to minus 3. So it is rather small. When we assume that that reconnections are universal, and this angle is as calculated by Varela and Arts is 25 degrees, then μ is 0 and it makes no sense. When we take the best result of recent result of Carlo Barenghi, when we can find that it is quite frequent that reconnections became, that lines became anti-parallel just prior to the reconnection. And we can, right, this is the final slide. And this mechanism can be quite efficient. So I think that there are like 3 classes of mechanism of energy dissipation we have. So one mechanism was proposed by Feynman. Feynman really looked forward because he proposed the mechanism of vortex dissipation before the vortices were discovered, in fact. The other mechanism was proposed by Svistunov in a series of papers starting from 95. It goes through reconnection. That reconnection produces waves on vortices called kevlons, and this leads to dissipation. The problem is that the dissipation via kevlons decreases as time to minus square. So unless the reconnections are very, very frequent, this mechanism cannot be very efficient. And then there is the mechanism we propose. Here the length dissipation after single reconnection decreases as 10 to minus 1/2. And this mechanism can be efficient provided that reconnections leading to cascades of rings are frequent enough. Thank you. I'm sorry for...
Okay, I'm a little bit embarrassed because I have a problem. Now we have another talk, very short talk, which is planned. And because of the schedule, is this question that important, or could you keep it as a private question, if you don't mind? Because no Stefanella has going, or maybe during the time, Stefanella, are you going to use a computer? Okay, so during the time that Stefanella should log on the computer, yes, please.
Yes, me? Yes. One of the assumptions of the local induction approximation is the ratio between curvature length and core radius is constant.
Right.
Yeah. So if you have very small curvature, so then you have to change the core radius, which produces the speed of filament.
Right.
Yeah. So are you? Do you take care of such kind of things precisely, or you just use the same
we are
constant?
No, we are neglecting this, and to check it, we do the Biot-Savart simulation and then Gross-Pitayevsky. Seems that the fact that these results hold under Biot-Savart and Gross-Pitayevsky is because everything is set by the asymptotics. So if the structure has a given asymptotics, then these rings will be generated.
And also they quickly converge to a solution which has constant curvature, which avoids that problem.
Oh, I see. Okay.
Well, thank you very much.